Thank you, Dr. Srinivas, for inviting me for ATAL workshop to deliver a lecture on visible light communication for 5G and beyond. And one correction from my biodata, she mentioned 6 PhDs. I completed 10 PhDs right now. So, and all of my students, those who completed PhD under my guidance, all of them are in NITs and IIITs. And one student is in IIT Amravati. And so today's my topic is because you people are far away from this place. I don't think you don't want to see the technical content of this session. Please come forward. Okay, please settle down. So my area of specialization is in wireless communication. I mostly work in physical layer aspects, and also we demonstrated a test bed using visible light communication at NIT Warangal, as well as we have demonstrated a wireless communication test bed for 5G and beyond. And we are presently working in OTFS, that is orthogonal time frequency space modulation, and visible light communication, and IRS, that is intelligent reflecting surfaces. So you may be aware of all these topics earlier. From my previous, I could see the previous presenters who have delivered lecture on IRS and 5G wireless communication and many more other aspects. So coming to the visible light communication, I start with the fundamentals because many of them may not be aware about what is a visible light communication. So this visible light communication, we are seeing the lights in this conference hall. And so we are seeing lights in this conference hall, right? And when a tech fair is organized in your institute, can you provide Wi-Fi to all of the students who are present here? Can you provide them with the existing infrastructure? Yes or no? You cannot, right? Because the access point has some limitations. So you can give access to maximum 100 people as per your management acquired some data rate. So you cannot give a more data rate to the existing users when many people are gathered at one place. Also, here in this conference hall, there are many students and many faculty are here. For everyone want to access a Wi-Fi is not possible because there are certain limitations. Then what is the alternative technology to be adopted in 5G and beyond so that we can give access to all of the users existing in this network? So another alternative technology is a visible light communication system. So this visible light communication system works with LEDs. So you are seeing the LEDs on the top of the walls, which are giving illumination to this conference hall, as well as the same LED can be used for your communication. That's a new idea of, because the spectrum is already overcrowded, so I cannot add more and more infrastructure into the spectrum. More and more data rates cannot be allocated to the users. So only the alternate technology is a visible light communication. So this visible light communication, we use two devices. One is a LED light emitting device. So you can see in my diagram, one LED is, So LED is here. You can see the LED, right? And a photo detector. So these are the two devices. So forget about communication system first of all. For the time being, we are using LED. Through LED, I want to transmit a signal. So how you are receiving your signals from your mobiles? If you are using a mobile, this is a mobile. So when you are speaking in front of the mobile, the signal is captured by your mobile and it is sent to the base station. From the base station, again, it is sent back to the user wherever he is present, and alternately other side also, from the user it comes to the base station. From the base station, it comes to your mobile. This is the way the signal transfer is happening. Now, if you are using a visible light communication, the communication is happening between the devices, that is LED and a photo detector. So light emitting diode is one of the device. Instead of using an antenna, I use a light emitting device for transmitting your signals. For receiving your signals, we use a photo detector. So this photo detector, light falls on the photo detector. So when the light falls on the photo detector, it converts the signal into electrical signal. Okay. So this electrical signal is received demodulated, and we receive the signals into a form of a speech form. That is the same communication what we do in general processes. So the two devices what we are using in this communication system is the LED and a photo detector, right? So from the basic fundamentals of LED, so we know very well a light emitting device is works only when it is forward biased. Do you know or not? The current transmits through an LED, light emitting diodes, when we apply a forward bias to the LED, right? So this is switch is closed and we'll receive, suppose if I am keeping a resistance at the output, I can see at the output some V out voltage, right? That is a fundamental principle of a light emitting diode. Then now using this device, I want to use this device for my communication model. So how it can be done a communication model. So do you know what is the communication in front of, when you are speaking in front of the mobile, what kind of a signal you are passing on to this mobile? Is it your speech voice, right? That speech voice having a maximum frequency of 5 kilohertz. If you add some instruments, it goes up to 20 kilohertz of frequency range. That means your information is in the form of alternating currents, right? So your information is in the form of alternating currents. Just one example I am taking, that is a sinusoidal signal. Suppose if I am sending his voice, that his has a fundamental frequency of maybe 5 kilohertz. Okay, so this kind of a waveform I am transmitting through a diode. So now, is your diode can function for this alternating current? Yes or no? Will it allow this alternating current? So what I do, apart from, suppose directly if I use a diode and I use an alternating current source and I keep a resistance at the output, what is the output at this resistance for an alternating current? What is alternating current? My alternating current is a sinusoidal waveform. Let us assume that one period of sinusoidal waveform is given to this diode. So what is the output at the diode? So you already worked with devices, right? Half wave rectifier, full wave rectifier. So you have done an experiment by applying a sinusoidal signal. What is the output of the sinusoidal signal when you give it to the diode? So what you observe? You observe only half positive cycles. The negative half cycles are cut off, right? So that means your voice information is in the sinusoidal format. But if you want to use the same LED for illumination as well as communication, the obstructions what we are facing because of this forward direction conduction procedure, it can conduct only during the positive information, and the negative information we are losing. So that means what I am speaking in front of the device, it gives only half the information. Remaining half is lost. Then how to model your communication, because the light is very, very powerful source. So it is giving a light information to us, and at the same time I want to use it for a communication purpose, right? So one idea comes from this device is, suppose if you are shifting your information, that means if you add some DC source to this information, there is a possibility of your diode, because it conducts for only positive values, all the time positive. So if you add AC plus DC to your information, there is a possibility that all the time it can transmit the signal, right? So that means my device is now added with an AC source and a DC source, right? So can you, this DC source is around, so my AC is of 5 volts to minus 5 volts, and my DC voltage is around another 5 volts. So I'm adding these two. So what is the output at the resistance? What do you expect the output at the resistance? So this is two signals are in series. They are connected in series. When two signals are connected in series, is nothing but the signals are added, right? So AC voltage plus a DC voltage. DC is of how much? 5 volts plus upon 5, an AC sinusoidal signal is varying. That means your output source looks like, so now earlier it is 0, now it is shifted to 5 volts. Upon 5, we will see a continuous waveform. Now if we give this waveform to the diode, can it conduct or not? Because every time if you look at the waveform, every time it is a positive voltage only, right? So the minus 5 is now reached to 0 voltage. That means the diode is conducting. Okay, so we have to do some transformations to your signals. So if you can do some transformation to your signals, you can transmit your information through your devices. That's the meaning. So this topic was coined by Harald Haas 10 years back. So now it is 2025. It started in the year 2016. This only the small idea. Why can't we use a visible light communication, that is LED, as a device of for your communication purpose? So, but this communication is limited to only an indoor communication. I cannot use the same devices for the outdoor communication. Why? Because it is a light, right? So, what is a receiving device? The receiving device is a photodetector. So, photodetector, I am transmitting a signal to this device. So, light emanates. This emanated light is falls upon a photodetector which is present in this block, and this photodetector accepts the light and converts into an electrical form. But when you conduct this experiment outside of this building, what are the other light sources are falling on this photodetector? What are the other kind of sources are falling on this photodetector? Solar, right? The daytime light. So the daytime light is also falling on this device. So then that is called an ambient light source. So this ambient light source creates a lot of problem. Still this topic is under research. So no solution has come up how to eliminate the ambient noise using some filters. So people are working on it, but a permanent solution not yet came to eliminate this ambient noise. So this is now limited to only indoor communication system. So only in the indoor we can do this experimentation. And at NID Warangal also we did only indoor, and also we have switched off all the lights. We have placed only one LED and one photodetector. We could see in a wireless communication for a distance of 10 meters, the communication happened, and we could receive the bits what we transmitted from the transmitting line. We have done a physical experiment. Okay. So that is what the fundamental concept of a visible light communication. So this visible light communication, what I am saying is, in front of instead of your antennas, we can replace with these photodetector and a photodiode. Now So the system model we have to develop for this communication system. So already we have completed your analog communication and digital communication course, right? So you have already learned about we need to give some information to your source, then it is encoded. So encoding in the sense analog information is to be converted into a digital information, right? Then after converting into a digital information, we'll give it a modulator. So the purpose of modulation is also already well-known topic. So why we need a modulation, right? So the modulator, then we use the driver circuitry because I'm eliminating a antenna and I'm using a driver circuit and LED as my transmitting system. So this we are eliminating. We are not using any antenna source. So this antenna from this source, now it is modulated to pass through the LED and it is coming through the channel. The channel is a wireless channel. There is no link between, it is a wireless channel. And we also used an optical concentrator, but this is very costly affair. So maybe we have conducted an experiment without optical source and with an optical source. Okay. Then the receiver is used as a photodetector. Here a device is placed. We have used an amplifier and a demodulator, decoder and a data distribution. So the left hand side portion is same as your communication system. Only the right hand portion is changed to a driver circuitry, LED and a dimming circuit, photodetector and amplifier. Okay. So with this system model, now we can go for different modulation techniques. So these different modulation techniques, how many modulation techniques you have learned in digital communication course? Students, how many modulation techniques you have learned in digital communication course? No, no interest. Modulation techniques. BPL scale, binary phase shift keying. Yeah, you can ask some question. Phase shift keying, frequency shift keying, pulse width modulation is a partial analog and digital communication. Okay. Phase shift keying and frequency shift keying is more than enough. So that means a phase of the signal is changed, right? So when you are transmitting a positive signal, I use one phase. When I am transmitting another signal, I use another phase. So similarly, for visible light communication, we use single carrier modulation techniques, multi-carrier modulation techniques, other multi-carrier modulation techniques, on-off keying is another like your on-off keying and a pulse width modulation, pulse position modulation, and so coming to the multi-carrier modulation techniques, OFDM and its variants, and head-mod coded modulation is our advanced variants of modulation techniques. Okay, so mostly I concentrate on multi-carrier modulation techniques. So these multi-carrier modulation techniques, just give me, I'll open the file. Okay, so I'll talk about some OFDM technique. So what is this OFDM? Why do we use OFDM in your 5G and beyond 5G communication systems? So this OFDM is orthogonal frequency division multiplexing. Okay, so orthogonal frequency division multiplexing. So general communication system, if you observe, in a single carrier communication, what we do, we receive data bits, some data bits, and these data bits, suppose if I am using a binary phase shift keying BPSK, I translate into -1, 0 because 0 is not conveying any information. So we convert into +1 and -1. Then if it is -1, what I do? I generate a negative carrier like this. Okay? And to communicate a +1, I generate a positive carrier. This is a single carrier modulation scheme. Single carrier communication scheme. Now, OFDM, orthogonal frequency division multiplexing, is a multi-carrier modulation scheme. So what is this multi-carrier modulation scheme? Means there are many users in the communication system, right? So to give access to all of the users, each user must be given with a one carrier. So suppose I am communicating my signals over the air, I need a dedicated, so because each mobile has one number. So that number signifies how you are communicating your signal. You will be uniquely decoded with your values. Okay. So now this multi-carrier modulation systems, so many people asked to be added into the network. So each one must be identified with a different frequency. So that means each frequency is F1, F2, F3. Like suppose there are 100 users, each one is given with 100 carrier sequence. So onto these carriers, what we do, we modulate of each user's data. We modulate each user's data onto F1, the second user data onto F2, third user data onto F3. That is the one way of communication. And then we multiplex all of them into one single carrier communication. There is a one method. The another one is, what we do, we take the data and we multiply the set of data, each data with one carrier frequency, F1, F2 and so on, like F100. So these, because each one is identified with a different carrier frequency and they are orthogonal one to one. You know the meaning of orthogonality. So what is orthogonal? Suppose a cos 2 pi f1 of t is one signal and another signal is cos 2 pi f2 of t is another signal. If we integrate from -infinity to plus with respect to dt, we will get a resultant of 0. That is called orthogonality, right? So, is the sign carriers are also orthogonal? If I multiply sin 2 pi f1 of t multiplied by sin 2 pi f2 of t, are they orthogonal? Orthogonal or not? F1 and F2, two carrier frequencies. Let me take this example now. So here I am mentioning cos. Okay, here I am mentioning cos. So maybe I can mention a sine signal also. This is one sine signal with a carrier frequency of f1. So what is frequency? The frequency is nothing but time taken to complete one full cycle, right? So that is, I'll call it as 1 by this f1. This is my frequency, the time taken. I'll take another signal where the signal is having f2. 1 by f2. Now, if you multiply these two, what is the resultant output? Will you get a 0 or not? Each carrier, any cause two different signals, if you multiply, the resultant answer is 0. Why it is 0? If you look at, this is some value, this is 0. When it is going up, maybe this is somewhere else. So the total area, when you combine them, that goes to a 0 value. So this is, actually we have to write a formula of cos A, cos B formula, and we have to allocate, and what is the condition on F1, F2, such that the relation between F1 and F2 such that your cos product will become 0. We have to do the big derivation, right? So this is orthogonality. Now, when you are transmitting your signals, so these signals are modulated onto orthogonal in the form of orthogonal frequency division multiplexing. So this OFDM is a technology, it is continued in 4G and now we are continuing 5G. And you are also may continue in 6G with some more additions. Okay. So this, what does it say? The orthogonal carrier frequency. Actually, the data, what the data is coming. Suppose if you take a single user data, I want to transmit. So his data rate is required maybe around 1 Gbps. That means gigabits per second. 1 gigabit per second is the target data rate in your 5G communication system, right? So how do you achieve this 1 Gbps data rate? You know the relation between a data rate and the waveform what you are transmitting. So you know the time relation between frequency and time. The time and frequency are inversely related, right? So for transmission of your signal, for transmission of my, to achieve 1 Gbps data rate, I have to transmit my signal using a nanosecond time scale. So 1 by nanosecond, what is 1 by nanosecond? Will be in gigahertz, right? So 1 by 10 to the power of minus 9. 1 by 10 to the power of minus 9. If you translate, this will be in 1 into 10 to the power of 9 hertz. That means that is in gigahertz. So the gigahertz, gigabits per second I am transmitting. So that means to transmit a particular signal, I have to compress my time scale such that I can send my signal at a faster rate. That is the meaning, right? So every nanosecond I have to transmit my bits of data. So when you are transmitting every nanoseconds of time, what is happening in a wireless communication scenario? So very, very short time I am transmitting. So this short time of nanoseconds of time, when it is received through your wireless communication channel, what I receive 1 bit of transmission, I will receive a 1 bit of transmission. Apart from 1 bit, at because of the reflections, the scattering and diffraction and other effects, so I'll also receive some more signals like this at different intervals. Okay. Now this is creating what? So can I decode this signal now? What I have to decode? I have to decode this signal. But if you look at the signal, it is now contaminated with many samples of information. Now again I will send a second signal. So in the second interval, I am sending a second signal. So when I am sending a second signal, this second signal I will get a one replica and also I will get other replicas over because of non-line of sight communication. Now when I am receiving a second sample of information, the first sample information is already present in the channel. Is it not? Can you see this? The second sample is already present in the sample. So I will draw this one with another. So this is the second sample information. Now what is happening? The first sample information is now override with the second sample information. When I am trying to detect the second sample information, the second sample information is now the whole corrected with the first sample information. So now it is not possible to decode each single information at a given instant of time. So I am not connecting with most of the mathematics. I am explaining in a simple terms. So why, if you want to achieve a higher data rate, why it is not possible is because of this scenario in a wireless communication system. Okay, but if you take a long time of your transmission, I want to achieve a gigabits of data rate, but what I do, I divide this gigabits of data rate into smaller streams. So what I do, I'll take a longer time scale now. I'll take in milliseconds of my time. Okay? But now my time scale, earlier time scale is nanoseconds. So, but now I am taking a milliseconds of time. If you take a milliseconds of time, what is the data rate you would achieve in communication system? So 1 by millisecond, that is 1 by 10 to the power of minus 3 is only 1 kilobits, right? Kilohertz. So that means kilobits per second only I can achieve. But what is targeted data rate? The targeted data rate is gigabits per second. So how do you achieve a gigabits per second? But with this time scaling factor, with this time if I am transmitting, this kind of overlapping in the time scale is barely mitigated in this communication system. Okay, so even if we have a line of sight communication or a non-line of sight communication, what we receive at the receiving end is, if I am transmitting with this signal, now it goes with, even then there are multiple line of sight path components are present, but they come only in a smaller, like, so everything is coming only in this cluster. So this time period is very, very minimal. So when the time period is very, very minimal of the multipath communication system, this fading we can eliminate and we can decode your signals very easily. But whereas in the previous case, it is expanded in the time scale. So they are unable to decode the signals, right? So that is why we use to increase our data rate, we restrict ourselves into the lower time scale and lower data rate, but we send them in parallel. So 1 millisecond, so this is one, and similar another one, also we send, similar another waveform also we send according to the modulation. So like earlier we send every data in a bigger pipe. Now what we are dividing into smaller pipes. So like in a truck, suppose we have a big truck. In the big truck, you have dumped everything. Instead of that, what we are doing, we are making into smaller trucks and we sending the smaller trucks in the same line. So they go parallelly, one in the same line, dedicated line. So each truck is traveling in a parallel fashion. So each one is carrying 1 kilobits of seconds, right? Suppose 10 trucks are travel, 10 multiplied by 10 kilobits of second. Now, to achieve a 1 gigabit of 1 Gbps data rate, accordingly we transmit your signals. So we can achieve a higher data rate. So for that we need an orthogonal frequency division multiplexing. That means each track now takes F1 carrier, F2 carrier, like that it goes up to F100 carriers. That is the concept of orthogonal frequency division multiplexing. Okay. Now, so I explained about multi-carrier modulation and its variants. Okay. Now come to the orthogonal frequency division multiplexing. Why it is important in visible light communication? Because they have to be accommodated along with your 5G communication. So the 5G is using OFDM. So visible light also we want to achieve a high data rate. So we use this multi-carrier modulation. So now the limited modulation bandwidth of the LED is another problem. So I want to use multi-carrier modulation using these devices. But my device is very small, a small LED, right? So can it transmit your sinusoidal variations? Can it take the variations of the sinusoidal signals? That is a problem. So what is the problem? Look at the diagram, this diagram. So if you look at this diagram, you know the cut-in voltage and cut-off voltage of a diode, right? Cut-in and cut-off. So the diode can operate only a limited region. If it goes beyond that region, it goes into saturation. But your voice signal, we are transmitting some kilobits of second using an orthogonal frequency division multiplexing, right? So many variants of sinusoidal signals we are transmitting. Now that amount of current, can it be accommodated in a smaller region of cut-in and cut-off? Is not possible. We cannot accommodate every carrier into this cut-in and cut-off voltage region. So that is one of the limitation of a visible light communication. Okay. So this limited bandwidth is also enabled to adopt orthogonal frequency division multiplexing, but we will see how to eliminate those shortcomings of your saturation region using some other techniques. So we and already I mentioned, because the diode takes only positive voltages. So that means we have to ensure what we are giving to your LED is a real and a positive transmission of your signals. So please, I am seeing the students are maybe lazy to understand and they are not feeling that it's a useful topic for us. Better use your pen and note so that if you are writing something, automatically it goes into your mind. Always make a habit of, even a teacher also, always make a habit of, always when you go for a class, you go for a lecture, even you go for a common talk of a eminent any administrators. So don't go blindly with only open hands. You go with, or even you can use your mobile to open your file and note down the content what is going to explain. So that creates the coordination with your mind, coordination with your hand will create a balance of your the whole mind and activity. So that is how the foreign universities are ahead of Indian universities. So their activity is always a mind and hand coordination. They do a lot of activity. But whereas we learn only by hearting the system, by hearting the signals, by hearting the so many variants. So every time we do only impractical. So we don't want to see the practicality. We'll only digest the things. So that is not a good habit of learning. Always learning means use your pen and notebook. So even if I explain without my pen, I don't go to the board. I don't explain to anybody. I always use my pen. So I can play a PPT, right? What is fun? Everything is available in my PPT. So I can keep on talking on the looking at the PPT and I can explain this is what happening. This is going further. This is what. So, but I never use that practice. I always use something in between I write, so that my mind balance is happening when I am doing this activity. Okay. So please, all the students, make a habit of in your life. That is a fundamental habit. Use always your mind and hand coordination is very much important in your practical life. Okay. Now, so what I mentioned, are there any doubts till now? Okay, no doubts. So always make sure that when you are using these devices for communication, you have to prepare your signal into only a positive side. That's what I mentioned in my previous diagrams. So we use a DC and made it to the entire negative portion we clip to the above the axis. That is a positive signal. Okay. So now there is a one technique called Hermitian symmetry. Hermitian symmetry is one technique. This makes your signal always positive. So for visible light communication, we use a Hermitian symmetry is one of the transform technique. So this transform technique makes your signal into a positive real signal. So writing the equation for a OFDM. So how I modulate a signal. So here I am writing one signal, summation of here I am writing this equation. So n equal to 0 to n minus 1 x of k e power j 2 pi n k by n. This is called orthogonal frequency division multiplexing, a OFDM equation. So what is input? X of k is my input. So I already mentioned every signal is to be multiplied with one orthogonal carrier, right? So what is that carrier? The carrier is either cos or a sine, right? So here what I am using e power j 2 pi n k by capital N. So you know the meaning of e power, exponential signal. Exponential means cos plus j sine, right? Cos plus j sine. This is my exponential signal. So this already in your digital communication, you have learned how to represent a signal in a digital modulation scheme, right? So we use in the baseband in an exponential format, e power j's. So if you take the real part of e power j, that is nothing but your cos signal. That is nothing but your cos signals. Okay. So for mathematical simplicity, we don't use cos and sine. We use e power j's always in your communication system. Also, we handle your communication system in the baseband nature so that the analysis is becoming very easy. Okay. So here in OFDM, we use for each k is your, so k equal to 0 to n minus 1. That means there are n number of subcarriers. Onto the each subcarrier, we give a signal that is called x of k and it is multiplied by cos. Cos means e power j. That is your orthogonal carrier. Okay. So now we talk about Hermitian symmetry. So the applications of visible light communication, we use the car-to-car communication where car uses an LED for its focusing, right? When it is traveling on the road. So between the cars, we can use a light emitting diodes. Even your sensor signals, your traffic lights also, there we use a communication signal. So this, so I don't go to the higher order modulation schemes, but I concentrate on lower order modulation schemes. So one problem in I'll talk about the OFDM problems in later. So I concentrate on Hermitian symmetry. What is Hermitian symmetry? So this Hermitian symmetry, look at the waveform. So I am using n orthonormal carriers. So everyone can write down, we are using n orthonormal carriers. So the representation of the n orthonormal carriers, 0 to generally we represent by n minus 1. Okay. So these n orthogonal normal carriers, and each carrier, if you remember the previous equation, summation of n equal to 0 to n minus 1 x of t e power j, right? So unto each carrier, we modulate one signal, x1, x2, x4, x of n minus 2 minus 1, so on, like that. Okay. So this, in this Hermitian symmetry, to bring only a real signal, because if you use e power j, the output is only always complex. I don't want to see the complex. I want to see only a real signal. So to make it real, if you look at the organization of the values of your data symbols, how I am organizing up to n by 2. Look at up to n by 2 as it is. The first carrier, we are not modulating anything. And also to the onto the center carrier, we are not modulating anything. 0, 0. And x1 to x of n by 2 minus 1. Okay. Then after that, x of n 0, then we are modulating with a conjugate symbols. So x conjugate of n by 2 minus 1 in this order. Look at the other half. The half, so we have to take n symbols. So these n symbols we have to modulate onto n carriers. But what I am doing, I am taking n symbols, but out of n, I am making it as n by 2 symbols. I just take only n by 2. So in the first half, I'll give n by 2 symbols. For the half of the carriers, we just make the complex conjugates of the previous signals. Can you see this diagram? First half is as it is. But the second half, the same symbols are conjugated. Okay. So do you know what is conjugation? A plus j beta. Suppose x of 1, my x of 1, a plus j beta. Okay. Now where is my x of n? X of n is at the end. So what I supposed to give at this conjugate value? So the x conjugate of 1 is what? It is a minus j beta. Like that we are giving the symbols. Okay. So if you give this kind of a Hermitian symmetry, what is our objective? Our objective is the output should become a real signal. So we will see whether it is coming as how we are placing x of 0, 0, and the middle of the carrier also I am placing 0, and the Hermitian symmetry condition is x of n minus k n minus k is x conjugate of k. Could you see that x of n minus k is simply x conjugate of k? So go back. What is this one? X of n minus k. That means last value x of n minus 1, right? This is my n minus 1 value. So in that value, what I supposed to keep? The last value is x of capital N minus 1. This is my last value. What I supposed to keep? X conjugate of k. What is the k value? K value is 1, right? That means I keep x conjugate of 1. Satisfied? X conjugate of 1 is satisfied, right? So we keep x of n minus k is equal to x conjugate of k. So now how many k's I am using actually? N we have taken, but our data symbol is only half. That means your k is running from only half. So k equal to 1 to n by 2 minus 1. This is the arrangement of my signals. So first location 0, central location is 0, half the values, the remaining half are all conjugates. Right? So now write down the whole equation. So what is this equation? This equation is orthogonal frequency division multiplexing. That means summing up all the values. What is the resultant value output? The output is a time domain signal. The output is a time domain signal. So that is x of n. What is my x of n? Is summation of x of k e power j 2 pi n k by capital N. Right? If you open the equation, so x of 0 is 0. I did not keep anyone. X of n by 2 is also 0. So these two are going away. And so I am keeping into two separate sections. K equal to 1 to n by 2 minus 1. And remaining is k equal to n by 2 plus 1 to n minus 1. X of k to power j 2 pi n k. So now we will play on this the second value. So how we place the second value? We place conjugate symmetry, right? So for the remaining half, we place the conjugate symmetry. So if you arrange that conjugate symmetry, that is x of k e power j 2 pi n k by n, the remaining separate half. So now look at the first half as it is. In the second half, I made n minus k. I'll call you later, okay? Okay, so now, x of n minus k as another variable is introduced so that it is changing into this format. Now, if you combine, because n minus k is nothing but conjugate value, so the conjugate value is inserted, e power minus j 2 pi.
Or we can continue till 12 o'clock, we can find out.
That is your wish, their wish. No problem.
We can continue 12 o'clock, we can find out.
Do you want to take a break or? So only 5 minutes. Okay? వాళ్ళ కోసం అంతే.
ఈ టైం టెక్నాలజీ అంతా కొద్దిగా కట్టుకుంటారు అందుకే చూస్తున్నారు.
రికార్డింగ్ పంపాలి కదా.
అదే
అది రికార్డింగ్ ఆపమని.